Hello, so this is my video for my project. I've got a few questions on the DLE that I'm going to answer in the video. Why were you looking at this? I'm very interested in machine vision. I want to improve my C++ coding. That's definitely happened. I really enjoy sport as well, and golf, and the application for machine vision in sports complexes. You can practice by yourself, eliminate the need someone to be there. You know, it's pretty compelling. You could get better at sports by yourself, facing a robot, which is very cool. For example, like a robot goalkeeper, using the same technology that I am showing here. It basically exactly the same, just instead of a hole, you'd have a plate and a goal behind it. What were the issues that needed solving in this software? There were so many issues with Qt, because it's all real time, getting Qt and Ember to work together. That was a pain. Qt as well itself is not the nicest IDE to use. It has a bunch of functions that work in the background that were messing with Qt, like the serial port libraries, and took hours to fix because they were just nonsense errors. And also, I guess getting the drivers for this camera. It's a PlayStation camera, PlayStation Eye. It doesn't work on a computer unless you get drivers, which some lovely man on GitHub posted them to GitHub, so I'm using his drivers. Credit to whoever he is. Who will benefit from this system? As I say, sports application, athletes. It could also be used in conveyor belts for color segmentation, putting different pieces on one side of the conveyor belt. The same hardware can be used to do that. Just have a camera, separate by color or separate by objects. What savings will it offer? It can definitely save money in a conveyor belt system. Instead of paying for workers to do it manually, you get a robot to do it, saves you money over time. And it also saves the ball from going out of bounds. So, what am I proud of? We'll start off with we'll start by running it, and I'll explain it as we go. I'm using a power supply to power this stepper motor. I was using a charger, but it wasn't maintaining a high enough current, and it made the inertia made it miss steps, and it was incredibly inaccurate. But that problem is now solved. So, this is my start menu. I have a GUI class, which instantly loads this, gives you the options that you can put, and then it waits for user input so you can get your options, right? If we press option 1, test. Now this will send a 1. If we go here into the main loop, option 1 will write 1 using my STM serial port class. So I'll take you through the classes now. Here is my detection class. My detection class has everything to do with detecting everything. So my detect ball function, member function, converts the frame, the current frame, to HSV color space, and then checks the white bounds. Anything between those bounds is displayed. Then this is all morphology, eroding and dilating. It removes background noise in the image. The green detects the green, which is this. It does the same thing, HSV color space, checks within the bounds, displays it, does morphology. Then it resizes the image to 1 pixel width and brings it back out after to normal size, resizes again. This basically averages out the boundaries on the Y coordinate, because this boundary here could be maybe 5 pixel width difference on the camera. Just squishes it into 1 and then expands it again. It keeps it a dead straight line. I will show you this working. The boundary detect member function is really cool. It takes in the green, the masked edge, which is from the green detect. It has a for loop that goes down. It initializes the boundaries array. It has a for loop that goes down, and every pixel checks to see if the pixel value changes. Now -1 means white, and white on this masked edge is where the green is. So when it reaches -1, that's the top boundary for the green, bottom boundary, and it stores it into the boundaries array. Then, for loop again, starting from the position we just reached. And then if the pixel value changes to 0, that's the end of the green, store that position. The boundaries then are checked to be within a sensible amount between 2 and 478, and if they are, the boundaries are returned. If not, then we keep looking for boundaries. Okay, and when we say collecting boundaries has failed, we just return the boundaries as 0, 0. It keeps doing it until we get boundaries that are proper. I'll quickly show the GUI class. Literally display start, cout displays a start menu. Get user input, blocking, using a loop, keeps looking, uses the continue to make sure that choice is equal to one of the valid options. If it's not equal to one of these valid options, it continues and gives you a little error message. When you do put in a 1, 2, 3, 4 or 200, that's there for testing purposes, it returns the choice. So, my serial port class, very, very cool. The constructor here creates a new queue serial port object, and then gets the number of available serial ports. Okay, tells you how many there are. Usually it's 3 on my laptop. Then for each of these available serial ports, it checks to see if the vendor ID and the product ID are equal to the same of my STM board. Now before, I had a little function that looped through and got the vendor and product ID of every available serial port, and it only does that if there's something connected. I only have my STM board connected, so I knew that the ones that appeared were my STM board. I saved them in the header file as constants here, and now I'm looking for the STM vendor and product ID here. If it's found, it saves the port name that it's on, and it sets STM available to true. Tells you the board is detected. If the board is available, it configures the port. It sets the port name to the one that it just found, which is really cool, dynamic, and then configures the rest of the port, opens it up to write, and then these are some checking just to make sure that the communication's open and tells you if it's failed, that sort of thing. Write data here is my writing data to the STM board function. Takes in the data as a string, concatenates an S on the beginning and an E on the end. These are special characters that start and end. This shows the STM board when to start and stop reading the data. If it's writable, write the data, convert it into a character, pointer to a character, and then send that pointer, send the data. And also we've got a wait key here because it's sort of like an update function. It makes sure that everything is sent, and a little else to say if it's written or not. So, choice 1 writes choice 1, choice 2 writes a 2, choice 4 doesn't write anything, it just sets up my boundaries, which is really, I'll show you that function, very proud of that. Choice 3 basically uses the bool detect, resizes the frame to 640 by 480, so I have a higher FPS. Detects the bool, has the bool detect frame, and then uses moments to work out the center of gravity of the bool. So this is saying if there are moments on the frame that I'm looking at, to create a point, M10 divided by M00 is basically finding, like, these all both represent spatial order, first order spatial moments of an object that are used to calculate the center of mass, and they're like the X and Y coordinates of the center. So when they're calculated, we draw some lines 25 above and to the side of the centroid, just so on the frame so you can see where the center of mass is being detected as. And then we draw the lines on those points. Then we check if the center in the Y coordinate is between the boundaries that we've found, and if it is, we work out the float, which is the fraction from the bottom boundary to the bool. It's like a percentage, like just 0.4 if it's 40% of the way across the green. It'd be like here. then it works out the exact step by timesing by the maximum steps on the linear actuator, which is 1,200. If a step is not the current step, so it only sends if the ball has changed position, and then it says ball is at step, sends the data, okay, using the serial port, and then it updates the current step to the step. Right, so that's my Qt side. My embed side, which isn't open because it can't be open when I'm loading the project, so I'll just show this to you first. If I press 1, right, and send 1 by pressing enter, it's going to move my motor ever so slightly to the right. I'm just going to set this at the 0 position here. It has to be start here. So I press enter, I press 1, it's just going to move it right and left. That's just to test that it's working. Now, if I reset my STM board, I can send a 2. Now, old reliable is going to send the gantry from one side, the plate to one side to the other. Just a small little fun game to play. I can have a hole I will have a hole attachment here on Project Showcase Day, and the hole will move from left to right, and it will be a game that you can play. Try and get it in the hole, just like a fun golf game. Now let's restart this when it gets to 0 position. There we go. There we are. Now I have to set the boundaries, so I send a 4. This is really cool because it looks at the camera image, which was a little bit incorrect, so I'm gonna reload this and just make it a bit easier. So sets the boundaries. Oh no, that was the wrong way. But you can see it in there, collect boundaries failed, but when I move the camera to the right point, it detected the boundaries. That's quite cool, showing you that working. Just gonna move this to a correct point, set boundaries. Nope, that's too much. It's moving the camera and it gets the boundaries, so about there would be correct. So it's pretty cool. There we are, that's much better. So you can see it was kind of skew-if, but it's fixed that now. I did just accidentally bump the camera. The thing is with this method is the camera has to be the exact same place, or you're basically getting incorrect boundaries. There we are. So 65 and 399. I will show you that this straight green image, I can't load these because they're not updating the frame, so they technically don't exist, but this green image here is just a straight version of the green, which was detected here. Gives me some nice equal boundaries. I would blow that up for you, but I can't because literally it's not responding. Here's the HSV image. Yeah, so now I can do never miss, send a 3, and this is going to be looking for white, which will be the ball. I'll also get the camera feed up there for you. And down here will be either ball out of bounds or the coordinates of the ball. So let's get the golf ball. Okay. And I'm hopefully going to show you this working. First time. Let's have a look. Nice. So yeah, as you can see, it's pretty accurate. I'll give it one more go, just to true it. Yeah, sort of moves the motor to the correct position. Yeah, it had a little bit of a wobble on there, just because it slowed down a bit. But yeah, it's working pretty well. It goes to roughly the right position. I do need to change the bounds a bit, but they'll be correct on Project Showcase Day. And I will show you now the correct steps, what's happening. If I put the ball in, you can see it's detected, but it's not on the green, it's out of bounds. Cross the green, start sending the steps. This motor starts moving. As I move the ball across, you can see it's kind of detecting my arm a bit there, but as I say, the bounds will work on the day. And then I go across and I exit the boundaries again, it says out of bounds. See? So very cool. And I'll just show you. Yeah, it's very nice. Maintain the steps quite nicely, actually. Usually have to reset it. That was okay. So yeah, that's my project working. I'll just show you the embed side quickly. Turn this off. On the embed side, I have made my entire library to run the motor. There's my class for running the motor. This is a 15-minute max video. I don't know how I'm going to do this in 15 minutes. Answer, I'm not. I'm going to do it however long it takes. Sequence runs it clockwise, sequence run it anti-clockwise. There's 4 steps in the motor. This does 4 steps because every sequence is 4 steps. This was a serial port test, just echoing 200 back. This here is my simple move function, which makes the entire rest of my class redundant because it's so good. It basically just makes the takes in a target position and moves the motor to the target in steps of 12. It's a much smoother motor control. It stops it from losing steps as well. Yeah, as you can see, it's got a hysteresis of 10 to make sure the motor isn't moving any less than 10 steps, which could make the motor lose accuracy. It's not going to move 1 step. So yeah, just a bit of a bounds there. This makes 1 rotation of the motor clockwise. This one makes 1 rotation of the motor anti-clockwise. Phase per 400 steps is 50. This should be 50. There we are. Accelerate and decelerate. I was doing this function, but I don't need to do it anymore. But it was pretty cool. It had adaptive braking. Basically checked to see if it took in the total steps, accelerated, and then it checked to see if total steps was half of what it is, or half of like the current step. And if it was, it would start to decelerate. So that by the time you reached your goal, you would have stopped instead of like accelerating and then just instantly stopping, accelerate and then decelerate. And this is your decelerate. If it's on the decelerate, it will then increase the delay. And when you increase the delay in a stepper motor, it gets slower. Old reliable is what you saw option 2, just the motor going dunk, 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 dunk. Never miss is my machine vision one. Basically takes the midpoint of the ball and puts it into simple move. I did have the entire rest of my class was for this. It was so much more complicated. I was working out the exact movement needed, and then I'd send that movement to a different function. It would check if it's anti-clockwise or clockwise, send it into this function, it would move it clockwise by however many steps you've told it to move, and this one would do it anti-clockwise, and I had acceleration in here as well, but I've just decided to not do all of that. And then I have a serial port class here as well, which blocks, checks the serial port if it's readable. If it sees a S come through, it will continue through this if statement, clear the data string, and keep reading and storing to data until an E is read. When an E is read, it breaks out of the loop, and then you have data, which is turned into an int from a string, and you get serial int, which is your integer that's come through, which is the position of the ball, usually, or the option. And it will echo it back just for testing purposes. I had it echo back, and this does the same thing. It just writes to Qt. This is my echoing purposes. I was using this before. So yeah, my main over here is just option, takes in the option using serial read, goes into switch case. That's a small little test. That's the old reliable that moves from one side to the other. The first game mode. This is the machine vision game mode. And this just turns the steppers off. So, yes, that's my project. Sorry I've run over the 15 minutes a little bit. I'm out of breath. I couldn't talk about this whole thing in 15 minutes. Didn't know if I was supposed to go into that much detail, or if I needed more detail. It's pretty unclear on the website, the DLE, but I hope this is okay, and I can answer your questions at the Viva. So, thank you very much for watching, and I'll see you in the next video.